All right, this video is going to give some examples of and sort of reinforce the idea of quasi-experimental research designs, which is something we might do when we want to institute like a program or a training or some other treatment, but where we can't randomize people into groups. So for example, this is common in educational research where you can't randomly assign students into different classrooms or courses, but you can take two similar classes or two similar courses and give a treatment or a program to just one of those groups. That's the basic idea behind a quasi-experimental design. It's missing some element of a true experimental design, but it's still going to be better at giving us some causal evidence than a correlational study would be. It's kind of a middle ground when you can't do a full experiment. Now, the definition of a quasi-experiment, which literally the word means resembling an experiment, would be a study where the researcher manipulates a variable. So there is an independent variable, and yes, at the end we'll measure some dependent variable, but in this case what's missing is we're doing it without random assignment. This is really important because it means even if you have a control group, those groups don't start out equal. Like if your study has an experimental group and a control group, there will be a bunch of pre-existing differences between those groups in addition to the experimental treatment that you administered. So all of those pre-existing differences are alternative explanations for whatever pattern you see in your data at the end of the quasi-experiment. Which is to say, when you measure an outcome, a dependent variable, if there is a difference, it might not be due to the independent variable. That's what makes this kind of design so much weaker than a real experiment. But as I said, in some cases, we just don't have the power to randomly assign people to conditions, but we still want to compare some things and, before and after some intervention and have some evidence or some idea whether it might be working, rule some possibilities out. So the simplest, the most common form of quasi-experiment, even though it's kind of weak as a basic design, is just a pre-test, post-test design. With that, you just take one group of people, so there's no control group in this one, and you just measure those people, then give them your treatment or your intervention, and then measure them again at the end. So for example, maybe some company sells a brain training app. They might want to carry out this kind of, we'll say, half-assed sort of research to try and make some claims, some scientific claims about their brain training app. They want to say maybe that it improves attention. So they do this study and they just give 100 people an attention test first, kind of figure out where people are at baseline. Then they have these people play their brain training game for a month. Then they give everyone an attention test at the end. Of course, there's some serious drawbacks to such a simplistic study design. So pause and see if you can identify some of them. Well, for one thing, they might be doing better, the participants might do better just due to what we'll call practice effects because they took that first attention test previously. We actually call this testing effects. It's one of the threats to internal validity that we always have to look out for with possible explanation for the improvement that we saw. Or they might do better just because people improve in attention as they get older. Like we might call this threat to internal validity, we might call it maturation, right? People just mature or grow over time. Maybe they just get better over time. Now this one might seem a little weird in the context of our attention study, but consider that the company might go out and choose, to test adolescents for their study specifically because they know that adolescents are already going to get better at attention tasks as they get older. So they might kind of cheat in that way, knowing this. Or maybe, some new energy drink got super popular right during the 6 months of the study, and it's the drink that's boosting people's attention in general. Just this kind of outside thing happening in the world that has nothing to do with our study's intervention. We call that history as a threat to internal validity, just like other things, going on in the participants' history, their experience. It's kind of happening outside of our study, out in the world, that affects our results. And of course, there are other threats to internal validity possible here, but one thing you may have realized, if you're looking at this, some people, you may realize the issues here could be fixed, a lot of these, not all, if we have a control group. So let's take this pre-test, post-test design and just add one extra element, a control group. Do the same thing, but now there's two groups here, so we call this a non-equivalent groups design. The name doesn't exactly roll off the tongue, but it kind of makes sense. We're taking two groups that are not equivalent at the beginning because we didn't do random assignment. And then we're just going to give the intervention to one of them. So for example, to test if praising children makes them participate more in school, you might identify two similar first grade classes, and maybe you even check that they participate equally to begin with. So at baseline, both classes have the same participation, although they might have other differences between them. And then for one of those first grade classes, you instruct the teacher to give a lot of praise, and for the other, you instruct the teacher to give very little praise. Then compare the participation numbers for those groups, using probably an independent t-test, to see if the first group had more improvement than the second group. This is clearly a better design with the control group now, right? Much better than our last one, because now we can rule out maturation as a threat to internal validity, since both groups should be maturing about the same as first graders. And history becomes at least less of a threat unless, I don't know, one of our classes also had other things going on in their lives that the other one didn't. Or in that classroom, besides your intervention, something was going on that made that class's experience different during the study. And of course, both groups are now getting an equal testing effect, so that kind of threat to internal validity isn't as big of a deal because we're having both of them do a pre-test and a post-test. So if the treatment group scores is better at the end than the control group, it at least can't solely be due to a testing effect. But one of the groups here might naturally mature or improve faster than the other because the groups were not equivalent at the start. The groups might have differed in some ways, probably in many ways. Despite starting with similar participation levels, some other stuff about them might be different. Maybe one of the classes just happened to have more rich kids in it, like from the start, and they overall had access during the whole year to better nutrition, more sleep, and so on, so they just progressed faster during their first year of full-time school. So there's one more kind of change or improvement we can make to this basic design to get it a little better. It's going to solve a couple more problems, but still, not everything. So we discussed this in another video where I introduced it as the Solomon four-group design, but often it's just called a four-group design. So this is doing the non-equivalence group design that we saw a moment ago, but combined with a version of the non-equivalence group design where there is no pretest. So this way you can measure how much change there was independent of testing effects. After all, if you compare group 1 to group 3 here, it'll give you an idea how much that extra pretest for group 1 made a difference, how much testing effect there was. Likewise, if you compare group 2 to group 4, the only difference is that group 2 got that extra pretest practice. So you can see how much difference that testing makes. Then by subtracting that, you could see how much the treatment itself changes things. An example here might be identifying four, similar battalions of soldiers. Two of them get measured beforehand, and then one of those plus one of the unmeasured groups gets some new training program that you're testing out, and then you measure all four groups, so them plus the control groups at the end, and make some comparisons. But as I said, this doesn't fix all the problems we've mentioned. So the four-group design, it's a great solution to rule out testing effects as a threat to internal validity. But as we've laid it out here, it's still a quasi-experiment because, again, here they weren't randomized into these four groups. So in our example, all four of these battalions, they probably started out with a lot of other pre-existing differences. We have no idea if one of those things, something maybe happened to one of those groups or whatever. So the ones that we happen to give the training program to, maybe those were also the groups that would have improved more during that time anyway. Maybe they happen to have more of the type of people that would have been highly motivated by some political news that came out of that time, or any number of other differences. So we're stuck sometimes with a quasi-experimental design just because we're not able to randomize people into groups, but we can still maybe think up some clever ways to continue making our studies stronger if we're going to do a quasi-experiment. So there's some other possibilities. One example, people have tried what's called a switching replications design. This one's pretty clear when it's diagrammed out like this. You've got your two pre-existing non-equivalent groups. So you got your group 1 and your group 2, and you give one of them the treatment but not the other. So it starts out like any non-equivalent groups design that we talked about a moment ago. But now you do kind of a bonus round at the end where you're going to replicate your experiment, basically. Or your quasi-experiment. You're going to replicate the start, but now you're switching which group gets the treatment. Hence, it's a switching replications design. So for example, if you're studying whether playing bingo improves memory for older adults or something like that, maybe you measure memory scores of everyone at a couple, similar retirement facilities. Then you go and you implement a bingo night at facility 1 for 6 months and measure their memory scores at both places. This is where a basic non-equivalent groups design would stop. We'd be like, okay, facility 1 has more improvement than facility 2. Great, it's promising. But now we're going to flip things and do the bingo night at facility 2 for 6 months. And then, again, measure things at the end at both places. So this design is, it's also popular when it'd be unethical not to give both groups treatment. So if you don't want to deny the program, the treatment to half of your participants, then this design ensures that everyone gets it at some point during the study. This is also a popular design in places like schools, where things get repeated or start over at regular intervals, like a semester system or something like that. Imagine you've got limited resources as a school or as a school district. If you have limited resources for testing your new school program, you could just implement it for only half of your students one semester, or maybe half of the schools in the district, whatever. And then you do it for the other half the next semester. So if it turns out the program works, then everyone has gotten that benefit, but you only had to spend half of the resources at a time. Now, another type of study might look something more like this, what we call an interrupted time series design. So you take a lot of pretest measurements, kind of at regular intervals, you're measuring something just to get a feel for what it's normally like. Then you institute some change, like a treatment or a program or a new way of doing things. Then you keep doing that measuring at regular intervals to see if there was a lasting effect. So for example, examining if a new law decreased fentanyl deaths, you might be tracking those numbers every year for a few years. Then you introduce a new law. Then you keep measuring fentanyl deaths for the next 4 years and see if it's gone down significantly. Or a real-life historical example, back in the 70s, a big phone company, so Cincinnati Bell, they started charging 20 cents per call to the info service 411. And they'd been tracking it for a long time. For like 90 periods they'd been tracking prior to this. And then they instituted the change. They added this cost, and they kept tracking usage for 90 more periods afterward. And it was clear there was an immediate and long-lasting drop in calls to 411. So they assumed the charge probably caused that. They had made that difference. Now, what's a big limitation of a design like this? You might pause and think it through if you didn't notice it initially. Well, history, meaning the influence of outside events that could totally explain any change that happened right around that time of the treatment. Something else could have occurred right then, and that thing is the real cause of any change we see. So this is, again, that history threat to internal validity. Another way to think of it is that the data we get, it isn't going to be very conclusive. Like imagine we get this beautiful data here. You've got some observations and they're all kind of around the same spot. Look at these first observations. It's pretty consistent, right? There's not a ton of variation. So we're like, yeah, we know how this thing works at baseline. And then we do our treatment. So the X here is our treatment being instituted. And then you do more observations. And sure enough, there is a clear change after our treatment. So that would suggest either that our treatment works, cool, yay, or that something else happened at that point in time, at the X time on the chart there. Now, meanwhile, if the data comes in like this graph, it's not very useful as evidence for anything, just because it's not clear there is a change, right? There was so much variance to begin with that it's hard to tell if there's a consistent pattern that's different afterward, so that wouldn't help very much at all. Meanwhile, though, we might get data that instead looks kind of like this one at the bottom. So here, there's clearly something new going on right after the treatment, but it just doesn't last very long, right? So that might suggest that our treatment has an effect, but it's a short-term effect, kind of not very long-lasting, or that something else happened at that time. So you can see how no matter what our results are, no matter what our interrupted time series design finds, we can't be sure that our treatment is what caused it. So how do we get rid of history? Well, there are some things that can be kind of improved. So, for example, a multiple time series design, it's the same idea as the last one, But now you've got two groups that you're watching over time. Imagine they're basically the same. Over and over and over again, you're measuring and they're the same, at least on the dependent variable, right? So these are different groups of people. They're going to differ in some ways, but maybe they're at least similar in performance for the thing you're watching that you care about. Then you introduce the treatment to one group and not the other, and you keep measuring and see if the first group has some change, but also ensure that the second group doesn't have change, right? Because they didn't get treatment. That, if you saw that, would rule out much of the threat of history to internal validity, at least for any outside events that were common to the two groups. So an example might be our high school gym team versus our rival high school, a different gym team. You've got the results from the first 10 meets and you're looking and you're being like, damn, both teams have very similar performance. Like the whole year, we've basically been in a dead tie with them, the same level of skill, same level of performance. Then we institute a new treatment, a new thing for just our team. We give our team mindfulness training or something like that. Then we measure the performance of both groups afterward for the next 10 gym meets. And I don't know, you can look at the graph here for one example of what might happen. If we see improvement in our team, that would be the line in black here. They got the experimental manipulation. But if we don't see improvements or change for that other team, the blue line here, then it can't be due to anything that both of them experienced, any kind of common history. Like, for example, maybe the U.S. gymnastics team was in the Olympics that year, right at that time. Then that's kind of a motivational boost to see the U.S. gymnastics team in the Olympics or really killing it in the Olympics at that time. But both of these high schools would have had equal access to seeing that. We can kind of rule that out because that would have jumped the blue line up too. So we can say, okay, it's not something external like that. Makes it a little more likely that, yeah, it is our experimental manipulation that caused this difference. And of course, the study results might turn out more like this. Both teams get a boost at the time we give the treatment. That would be pretty clear evidence that our treatment didn't work, even though our team improved right afterward. But, if we didn't get any more treatment than the people who never got our treatment at all, then probably our treatment's not doing anything. Well, let's try adding one final change to make things even better here. So this last one, this will be the last example in the video, but it's called a staggered time series design, and it's going to help us shore up some more of the weaknesses of these other designs. So imagine now we have 3 or even more than 3 groups that we can monitor over time and see where their performance is. Then what we do is we introduce the treatment to each group, but at a different time. So we can see if they each improve at the specific time they got the treatment and only at that time. In which case, logically, it becomes more likely the treatment is actually the thing causing the effect, rather than, say, outside events that are happening at one point in time or affecting one specific group more than another group. So, for example, maybe you run 3 similar hospitals and you want to test if a new policy is going to improve waiting times in the ER. First, you would start collecting waiting time data for a few months, just get the baseline for all these hospitals. Then you introduce the policy first at one hospital. So you introduce it at each hospital at a different time and watch how that first hospital's wait times change and make sure the other ones don't at that time because you haven't changed the policy there. So if the measurements were kind of very steady across time, but then they go up and they stay consistently up after treatment and only after treatment at each place, then that would suggest the treatment may have caused the change. So we'll stop there for now, but the big picture lesson to take away when it comes to quasi-experiments is 1, they involve manipulating an independent variable. In all of them, we did something, instituting some treatment or program or experimental manipulation. But 2, what they are missing is random assignment. We don't control who is in each group, so there's likely a lot of pre-existing differences, even if we try to find very similar groups that match in a lot of ways to start us out. Now, no matter what we do with these, there will always be some alternative explanations for the data, especially since we didn't randomly assign, but we can rule out many of those alternative explanations and sort of remove or at least minimize some threats to internal validity. So some quasi-experiments are going to be stronger and have better internal validity than others. Now, in general, most of these designs could be turned into actual experiments if we just added random assignment at the start. Make those groups start the same. But in reality, quasi-experiments are probably more common in the real world just because it is easier, it is cheaper, it's often just more feasible in many cases to apply something to some pre-existing groups, rather than try and set up or control who is in those groups in the first place. So when true experiments can't be done, a good quasi-experiment can provide at least some suggestive hints at causation by ruling out some of those more plausible alternative explanations. It's often better than a purely correlational study where we just measured things.